So this experiment that was done in the 1960s with the two atomic clocks that were in sync, it you're talking about much less than a second, right? I mean, you're talking, it's really really small because the Earth seems like it's really massive, but you have to get to a really really massive object. Like for example, if you got close to a black hole, that would be a very noticeable difference in time, in the flow of time. Right? So, the closer you got to the black hole, the slower time would go by. And then right at the edge of the black hole, the time would basically stop. Right? In fact, that's how we define the edge of the black hole, called the event horizon. All right. So anyhow, that is Einstein. All right, so we mentioned that there is this matter that is causing the let me start with this. The ordinary matter that you and I are composed of is, of course, protons and neutrons and electrons that form atoms. The atoms form molecules. That anywhere from planets to stars to people. So that's ordinary. Ordinary matter is the stuff that we find on the periodic table. All right, but when we look out into the universe, when we look out into well, it started with our galaxy, as a matter of fact. When you look at our galaxy, the stars at the edge of the galaxy, in the spiral arms, the most distant stars are moving faster than if you just added up all the mass that is observed. They're moving way too fast for that. So there is there's something out there that's interacting gravitationally, but it's not interacting with the electromagnetic force. In other words, not with it doesn't interact with light or any form of light. And so it's called dark matter. Matter because it's interacting gravitationally, dark because there's no interaction with the electromagnetic force. All right, so it surrounds our galaxy, and then as time has gone on, we find that it's surrounding all galaxies. There's this stuff called dark matter. So if we can't see it or interact with it, how do we know it exists? That's a great question. It's because of the gravity, the gravitational effect. Like if you looked at our sun, right? I mean, the sun is 99% the mass of the solar system. Most of the mass it resides in the sun. And so the planets that are closer to the sun go fastest, and then the planets that are further from the sun go slowest, right? That's just, that's the way it works. And so if we look at the entire galaxy, the matter that we observe is, towards the center of our galaxy. Then the stars at the outer edges should be traveling slower, but that's not what is observed. So here, let's read this. If we apply this idea to the galaxies, we would expect that objects closer to the center would be moving faster than objects at the far end of the galaxy. But that's absolutely not the case. In fact, the stuff at the far end is moving just as fast as the stuff closer in. And so we realized that there had to be this material, some kind of dark matter out around the galaxy. It's in what we call the halo. The halo is this region that surrounds the galaxies. All right. So anyhow, that is. So here's a nice picture of it. So here's a picture of the average galaxy. This is the luminous mass, the mass that you can actually see, and then the stars way out here. I wish this was a little bit bigger picture. The stars that are way far away from the center are moving just as fast as stars closer to the center, and so there must be some matter out here that's causing that to happen. That's causing those stars in the outer edges of the galaxy to be moving just as fast. And so that's been termed dark matter. And not only is it, do we know it's here in, that it's in the halo of our galaxy, the Milky Way, but every galaxy that we look at seems to have dark matter surrounding it. In fact, a lot of the theories nowadays that involve the formation of galaxies, we think that that's, where the dark matter was distributed during the Big Bang. Again, we don't know what this stuff is because, all normal matter that we know about, that we perform experiments on, that matter interacts with light. This stuff doesn't interact with light. It just interacts gravitationally. So we don't really, we don't know what it is. We're still trying to figure it out. But again, we don't know what it is because we can't, other than its gravitation, we can't perform any experiments on it. We just know that it's dark. That is, it doesn't interact. Now, and the other thing that we can do is we can actually map the dark matter. We know where it is, excuse me, around galaxies because, remember the whole thing about Einstein's, the bending of light near a massive object. Well, the dark matter will bend the light as well as the ordinary matter, right? And in fact, we find that there's a lot more dark matter than there is ordinary matter. Right? Oh, there's a better picture of it. So after the Big Bang, ordinary matter as well as dark matter began to clump together, and that's where the galaxies are forming. Let's see, ordinary matter loses energy, it clumps together and becomes concentrated at the center. So this is the theory of, that's an interesting theory of galactic formation. But I mean, overall, it's very sound. Like the dark matter and the ordinary matter kind of basically tell the dark matter will tell the luminous matter where to clump together to form galaxies. All right. And now here's something that is really, really odd. All right. So just understand dark matter is this whatever it is this stuff that surrounds galaxies and causes the stars at the outer edges of galaxies to be moving, faster than you can account for by all the matter that exists in the galaxy. All right, so around the year 2000 or so, there was some measurements. Remember, I talked earlier about the Hubble constant, h sub 0, and so the measurements were actually looking at type 1 supernova, which, and don't worry about what that. They were just using the type 1 supernova to measure distances to various galaxies in the universe. And they made a startling discovery, a discovery that, to be quite honest, took me years to accept when this first came out. I didn't accept the evidence for it at first, and then lots of other people didn't think it was right as well, and so they went and did their own measurements, and it turned out that there was actually two teams it was actually in 1999 when it first started, 1998, but in the year 2000 is around when it was published. So here's what they discovered is. Let's see, careful measurements of distant galaxies tell us that the universe is expanding. So about 8 billion years ago, roughly 8 billion years ago, remember the universe is 13.7 billion years ago, or it's 13.7 billion years, or somewhere around that. About 8 billion years ago, the expansion rate of the universe begins to accelerate. No understanding. We don't know why that happened. That just completely blew our minds. But of course, astronomers like to name stuff. And so the reason that the universe is has been expanding with an acceleration, um, which started about 8 billion years ago, has been given the term dark energy. It's kind now it's not this, all right, but some people have thought about it this way. It's kind of like a repulsive gravity, right? I mean, people have tried to come up with this, but it doesn't seem to work very well. But it's basically like all of a sudden, remember, the universe is this thing that's expanding, but now it's expanding a little bit faster. All right, so that's the name that we've given this. Remember, it's always there's some experimental evidence that shows this. There's got to be something that shows it. Otherwise, we wouldn't. People were perfectly content with the regular old Hubble's law, but when this came along in the year 2000, it was pretty controversial. But now, of course, it's completely accepted because more and more measurements were made, and it turned out to be right on, exactly the way it would, exactly what was predicted. So that's dark energy. This took place roughly. Let's see. Did they show you about 7.5 billion years ago? The universe begins to expand at an even greater rate. So you can see this kind of sloping up. And so this is the overall composition of the universe. Actually, let me go back just a second. Okay, for the universe, the entire universe, to accelerate its expansion requires incredible amounts of energy, right? I want everybody to it's almost unimaginable amounts of energy, so that when we sit there and we look at the overall distribution of everything in the universe, are the things that we know about, the hydrogen and helium and all the atoms and things like that, is actually less than 5%. Less than 5% of the universe is the stuff that we can point to on the periodic table. Okay. Roughly, because for the universe to expand in an accelerated manner, most of the universe is this dark energy. Again, we have no idea what it is, but it's the cause of the acceleration of the expansion of the universe. And then, of course, dark matter is the cause of the speed of the stars in galaxies moving faster than they should be, right? Or if faster than they should be, if all the matter is the matter that we observed, there has to be this dark matter surrounding galaxies for us to get the velocities that we observe in galaxies. All right. This last little thing is a little bit, and this is not like it's going to happen tomorrow or anything like that. Is what's going to happen to the universe as time goes on. There's two scenarios here. It's either going to die a heat death. That is, if the universe begins to collapse in on itself. Hundreds of billions of years into the future. Remember, the universe is only 13.7 billion years old, or ultimately what's called the Big Rip. That is, if this dark energy, because we don't know what it is and we can't perform any experiments, we don't know whether it's going to continue and eventually just kind of rip the universe apart in the future, or the acceleration will slow down and we'll collapse back in on ourselves. So we really don't know what's going to happen. All right, so it's not worth losing any sleep over or anything like that. More actually, I should say, this Big Rip is looking more and more likely right now anyway. But that doesn't mean in the future scientists are going to measure something that will counteract this. But right now it seems like the Big Rip is the most likely scenario with the measurements that we have.